Alright guys, welcome to the Binomial Theorem, and what we're going to do today is we're going to use Pascal's Triangle and the Binomial Theorem to help us factor, or expand binomials. Okay, so a couple things: essential understanding, a pattern of coefficients and the pattern a to the n, comma, a to the n minus 1b, a to the n minus 2, b squared, comma, a to the first, b to the n minus 1, can be used to write the expansion of a plus b and that quantity to the n power. That n should be on the outside. Okay? And so what this says is the first term and then a to the n minus 1, one term less, two terms less, three terms less, etc. And we'll get into talking about this pattern here. And that helps us with the expansion as one variable decreases, the other variable's power increases. Okay, secondly, to expand the power of the binomial in general, first multiply as needed, then write out the polynomial in standard form. And we'll see that a little bit later towards the end of the lesson with the examples. So the first thing we need to talk about is Pascal's Triangle. Okay, it was discovered by the Chinese in the 1300s and later renamed for Pascal himself. What it is a pattern that's used to determine the coefficients of the expanded binomial a plus b to the n. The coefficients, the numbers being multiplied to the a and the b value, or a number just being multiplied to any variable. That's what a coefficient is. Okay, so what I've done here is I've listed a few of the rows of the Pascal's Triangle. Now you think it would start with row 1, but it doesn't. Each of these patterns, notice how this is always a binomial. Okay, and these are the coefficients that would represent when we multiply these out. So for example, if you had a plus b to the first power, that's just a plus b, which the coefficient would be 1 and 1. 1 and 1. Remember that we learned how to expand a plus b squared. That's just a squared plus 2 times ab plus b squared. Well, the coefficients would be 1, 2, and 1. So we start with row 0. Row 0, 1, 2, 3, 4, 5. And the numbers in Pascal's Triangle represent the coefficients for each of these respected expansions. Now how you get each row or each value? Okay, you start with 1, and then you have 1, 1. And then you always start with a 1 and then add here. So 1 plus 1 is 2, and then 1 on the end. You always start and end with 1. So 1, and then 1 plus 2 is 3. 2 plus 1 is 3. And then 1 at the end. Here, 1, we start with 1. 1 and 3 make 4. 3 and 3 make 6. 3 and 1 make 4 and 1. Okay? Pay close attention to this last row. 1, 5, 10, 10, 5, and 1. If we look at the binomial expansion, if we were going to multiply this out, this would be very difficult using the box method. You'd have to do a plus b times a plus b, get an answer, times a plus b, get an answer, times a plus b, and you'd have to continue. Very tedious. So what Pascal's Triangle allows us to do is to get those coefficients we need more quickly. So two things that are happening here. Okay, here's the 1, 5, 10, 10, 5, and 1. That's from Pascal's Triangle. That's the fifth row. Okay, we start with row. Technically, it's the 6th row if you start with 0, 1, 2, 3. Okay, so those are the coefficients we saw from Pascal's Triangle. Those are in green. Okay, now this is where that first part of essential understanding comes into play. There's a pattern. Notice, look at a. You start with a to the 5th because it's a 5th degree. Look at the value of a. 4, 3, 2, 1, and finally 0. Anything to the 0 power is 1. Okay, so a goes down. Now watch what happens to b. There's no b. 0, 1, 2, 3, 4, and 5. Notice the b values increasing till we get to the highest power. And notice the first and last terms always have a coefficient of 1. So that's how we can use Pascal's Triangle to expand a plus b to the 5th power. So the other challenging thing can be, what happens if we had a plus b to the 11th or the 12th and we needed to find all those rows? So instead of writing out row after row of Pascal's Triangle, you can use the second part of this, the Binomial Theorem, which is n factorial divided by r r factorial times the quantity n minus r factorial. What we're really going to concentrate is on this value right here. We're going to use our calculator to help us out. And when we have n choose r. Okay, so, and I'll show you that. There'll be a video accompanying this that you can watch and see that. So let's look at an example of using the binomial theorem. Now we're not going to go super deep into this. Okay, we're going to go a plus b to the fourth. Now we could write out the rows of Pascal's triangle, but let's see how we can use the binomial theorem to help us. So we're going, the highest power is going to be 4, and let's just kind of look at what's going on. A to the fourth, third, second, first, and in the last one it should be 0. That a should be gone. It should just be b to the fourth. Okay, no b here. B to the first, b squared, b cubed, b to the fourth. Same idea. As one power decreases, the other one increases. So we're going to start with a 0 term. So you're going to start with 4 choose 0, and then the next term 4 choose 1, and then the next term 4 choose 2, and the next one 4 choose 3, and the last one 4 choose 4. So the binomial theorem can help us get the same coefficients that we did in Pascal's triangle. It's just not as tedious.
Lily Morton,
Okay.
if you're in the building,
So,
report to the main office.
using our graphing calculator, we see that 4 choose 0, and I boxed these in red. I boxed these in red because you know the first and last term always have to be a coefficient of 1. So 4 choose 0 and 4 choose 4, that's just going to be 1. Okay? And 4 choose 1 is 4, 4 choose 2, 6, 4 choose 3 is 4, and 4 choose 4 is 1. And notice the power of A goes down and the power of B goes up by 1 each time. Same thing if we do to the 7th power. We're using that n choose r, right? So we start with our 7, and we're always going to start 0, and we're going to work our way 1, 2, 3, 4, 5, 6, 7. Right? The 7, that's the power. Okay, how many power? What's the power? And then you start with 0 and you go all the way till you get to 7, to whatever that power is. Okay, A starts at 7 and decreases by 1 each time, all the way through. B starts at 0 and increases all the way to 7 by the end. Remember, the first and last term are going to be 1s. So you get a to the 7th plus 7a to the 6b plus 21a to the 5th b squared plus 35a cubed b to the 4th plus 21a squared b to the 5th plus 7a b to the 6th plus b to the 7th. So that's using the binomial theorem to help us. It's much quicker than trying to write out all the way to the 7th, that row of Pascal's triangle. Okay? Now, what happens if we have a binomial other than just a single term, or two terms, A and B, where the coefficients are other than 1? Well, it's the same idea, and we're going to use binomial theorem. However, this is that second part of the activity. We have to multiply. This whole thing is our A term. 5A is the new A, and 4B is the new B term. So we're going to the 4th power. So look, 4 choose, you start with 0 like we said. Watch, 1, 2, 3, and 4. These two are going to be 1 because the first and last term always have a coefficient that's 1. It increases by 1 each time, and notice our power, a to the 4th, a cubed. Okay? Whoops. So this should be, I had a little misprint there, I apologize. 5a to the 4th. 5a cubed, 4b to the 1st, plus, look at 5a squared, so the 5a is 4. 3, 2, 1, and it's gone here. Same thing. No b term here. 4b to the 1st, 4b squared, 4b cubed, and 4b to the 4th power. Okay, so then you have to, 4 choose 0 is 1, so you have 5 to the 4th and a to the 4th. Okay, 5 to the 4th, that's 625, a to the 4th. Now here, whatever this becomes, whatever you get here, you've got to multiply by 5 cubed times 4. So you have to combine 4 times 5 cubed times this value, and that gives you minus, or plus, it should be 2,000. Okay? Or minus, excuse me. Now, we get 2400 a squared b squared minus 1280 ab cubed. Okay? plus 256b to the fourth. So that would be our final result there, and it should be minus. I apologize, I thought it was plus there. It's a minus, so that changes some of these signs in the middle. Last example here, what happens if we wanted a specific term? In this case, we wanted the fifth term, and we're going to have y plus z to the 11th. Now, going out 11 rows, or 12 rows, excuse me, of Pascal's triangle would be tedious. So we'll just continue using that binomial expansion. You're going to start with 11, look, 0, 1, 2, 3, and 4. You can say, well, Mr. Bennett, that's only a 4. Shouldn't that be 5 when you're looking for the first term, or fifth term? No, 1, 2 terms, 3 terms, 4 terms, that's the fifth term. So whatever term you're looking for, it's always going to be one less because you actually start with 0. You're not starting with 1. So just be careful. Always the same thing. Whatever my power is here, my n, start with 0, increases by 1. Y in this case is the first variable. It's going to go from 11, 10, 9, 8, 7. Z is going to be 0 here, 1, 2, 3, 4. And so we're really looking at 11 choose 4, yz, or y to the 7th, z to the third power, which is 330, y to the 7th, z to the 4th. So that's the fifth term. Okay? In our last slide here, it's just in conclusion some things you could see from binomial expansion in Pascal's triangle, and the binomial expansion of a plus b to the n. Number one, there are n plus 1 terms. Okay? So if you're at a fourth power, there's going to be 5 terms, and that goes with that 0 rule when we talk about starting at row 0 or whatever to the 0 power. So there's always 5 n plus 1 terms. N is always the exponent of the first and last term. So if it's a fifth, a plus b to the fifth, you're going to start with a to the fifth, and you're going to end with b to the fifth. So the first and last term is going to be raised to the end. We'll skip this one really quick. The sum of the exponents is always equal to n. So if you have a fourth degree, if you add your variable powers together, that should be what equals n. They should. So if you're expanding something that's a fourth degree, if you add all the powers up on each term, it should be equal to 4 each time. In successive terms, the exponent of a decreases by 1 and b increases by 1. And this changes. A and b, you could have x and y, you could have different variables, but whatever your first variable is in that binomial, that's always decreasing by 1. Whatever the second variable is, it always increases by 1. So that's binomial theorem, and using Pascal's triangle to help us expand binomials a plus b to the n power. Just be careful, these only work for binomials. It's not a trinomial. I didn't give you a monomial. It only works for binomials. If you guys have any questions or comments, just type them below, or you can email me at nicholas.bennett@dc.gov.